The question says, show that the equation for gravitational potential energy A is equal to Gm capital M, small m, over R is dimensionally consistent, given that the units for gravitational constant G, so these are the units, G is equal to Newton meter squared per kg squared. Then this is mass and this is mass. So M and M are masses and R is the separation distance. So this is the question that we're going to do, or the question that we're going to answer in this video. Now, we need to find, or we need to show that the equation for this is dimensionally consistent. Now here, we are talking about potential energy. By definition, potential energy is the energy that is possessed by an object due to its position. Potential energy is equal to mgh, mass times gravitational field strength times height. And now we have been given this to say gravitational potential energy is given by this in this question to say it is gmm over r. Now we need to show that this is dimensionally consistent. So since we know that potential energy is given by this, let us, without even wasting time, let us call it as equation 1. We've started working out this. Then we know that this one is given by, let us call this as equation 2. Now this is energy and this is energy, so we can equate equations 1 and 2. So equation 1 is equal to equation 2. So from this, we can proceed as follows. Let's say G M M over R is equal to mgh. Now, in order for us to know if the equation is dimensionally consistent, the left-hand side must be equal to the right-hand side in terms of dimensions or units. But since we want to know if it is dimensionally consistent, we are going to ensure that at the end, we are going to indicate the dimensions for each side. If this will be equal to this in terms of dimensions, then we can say the equation is dimensionally consistent. So let us begin with the left. We have G M M over R. But G, we have been taught to say G is equal to Newton meter squared per kg squared. And 1 Newton, this is the force that is produced when an object of mass 1 kg is given an acceleration of 1 meter per second squared. This is the force that is produced by that. So this is the, in fact, in Newton, it is a unit for force, or units for force, newtons. Now, 1 Newton, as I said, it is the force that is produced when an object of 1 mass, or 1 kg mass, is given an acceleration of 1 meter per second squared. So, 1 Newton is 1 kg meter per second squared in terms of units, because it's the force that is produced when this mass is given this acceleration. Now, from this, I think we can plug in the values. We know that the units for mass, we have kg, and then radius, which is length, radius, we have it is meter or meters. So from this, let us plug in this equation. So let us replace G by this one. So we have G N M squared kg squared. Then we have here, it is kg for mass, and also this one kg for mass. And then we have R, which is simply a meter. And we know that this one is equal to this one, so we have kg meter per second squared. Then we have meter squared, and also, so this one, meter squared per kg. kg squared. Okay, let's put them in brackets. Then we have kg. Then we have meter. So from here, we are able to see that this one square, this one we are dividing here. So this and this will cancel, this and this will cancel, this and this will cancel. So what we're going to have is we're going to have kg. Then here we have m squared. Then here we have second squared. So in terms of dimensions, we have m, which is mass. Then here we have length squared to the power -2, since it is dividing. So on the left we have this. So let us now see on the right. So on the right we have mgh. So m, we have the mass in terms of kg. Then this one, it is the acceleration due to gravity or gravitational field strength, which is given by m per second squared, then m. This one, m and m will multiply, we're going to have m, or kgm squared per second squared. And this one will give us, in terms of dimensions, we're going to have m. Then here we're going to have l squared to the power -2. And this is on the right.